We all want to make our systems more efficient, more compact, more reliable, right? Those three design concerns are normally on the top of everyone's to-do list. One unsung hero making all of those design dreams a reality is our choice of MOSFET technology. Whether you're designing industrial equipment, automotive systems, power supplies, or battery-powered applications, selecting the right MOSFET can make a significant difference in overall performance. And as you undoubtedly have guessed by now, that's exactly what we're talking about today. Hi, I'm Amelia Dalton, host of Chalk Talk. In this episode of Chalk Talk, Jake Canon from Toshiba and I take a closer look at Toshiba's UMOS-11 power MOSFET technology. We also explore the innovations behind this latest generation of devices, discuss how their improved characteristics can help reduce conduction and switching losses, and examine the features that make them well suited for today's demanding power conversion applications. And before we get started, don't forget to click that link. There you can find even more information about this topic from Toshiba. Hi, Jake. Thank you so much for joining me.
That's Amelia. Great to be here.
Excellent. Okay, so we're talking all about UMOS-11 MOSFETs today. But before we dig into the details, where do these solutions fit into the overall product portfolio at Toshiba?
MOSFETs have been Toshiba's bread and butter for quite some time. The UMOS process, which I'll talk a bit more about, is one of our core products, but we have a very wide variety of products that fit around these MOSFETs, such as other discretes, including isolation, some small signal type devices, transistors. But in the analog space, we offer motor drivers, some linear ICs, power management ICs, and a wide variety of legacy devices, in addition to our digital products like microcontrollers, some bridge ICs, and some other cool ideas. So the idea is with Toshiba, you can kind of have everything in one. We're the broad market supplier that can support all kinds of applications. But UMOS is our bread and butter.
All right, so Toshiba is a global company with sites all around the world, right, Jake?
Yes, but at our heart, we are a Japanese company, and that has been a really big thing these days that we do all of our front end out of Japan. So some of our biggest fabs are our Kaga and Himeji fabs. They do pretty much all of our front end for our MOSFETs, and a lot of our back end is also done there. However, we do have a very large fab in Thailand that does a lot of our packaging as well. So given the global climate, this has been really beneficial to us, and it's allowed us to have a leg up on our competition with very strong quality and reliable products.
So Toshiba is also working on new 300 millimeter wafer production. Is that correct?
We are. And actually, this is a pretty big shift. So when you go from 8-inch to 12-inch or 300 millimeter, it's a big jump, right? When you talk about square law with circles, bigger wafer means more die. And that's a big thing for us, especially as we expand capacity. So in our Kaga fab, we created a brand new building for a 12-inch line. And as a result, this has increased our capacity by about 2.5 times. And this was a decision we made long before COVID and allocation kicked in. And this has come to fruition actually a couple of years ago. But we're almost at full capacity at this point and bringing in new products to this 12-inch line. But it's really given us a lot of flexibility that we really need these days. And it's timed perfectly with the growing AI data center market and automotive market. So Kaga has been a big thing for us. And I think it's a core part of our business moving forward. So it's really great to see these kind of investments come to fruition.
So when it comes to silicon technology in particular, what does the roadmap look like for UMOS-11 MOSFETs?
MOSFETs are a bit more complicated than you would think. So when we design a MOSFET in a process, which I'll talk a little bit more about what it looks like, but we have to design it for different voltages, right? Let's say a 100-volt MOSFET is different than a 60-volt MOSFET. They're used for different applications, but at their core, it's a very similar process. So for us, we wanted to iterate on what is already a very strong and competitive MOSFET process. So we went from UMOS-10 to UMOS-11. And right now we have a 100-volt process out, 40-volt, and 80-volt. And this is actually pretty critical, as I'll explain later. This kind of targets some of the most core markets that we're seeing in the industry these days. But the plan is to go robust with this, right? Go broad and bring in different voltages, say 60 volt, 25 volt, and kind of complete this big picture That way, if you're a power designer and you're doing anything that we would consider low voltage or high power, you would have a solution from us in our UMOS process. So there's a lot of good stuff ahead, but a lot of this UMOS-11 stuff is here today, and that's great news. So as an example of what this actually looks like, generation over generation, we always make improvements. However, every new generation doesn't necessarily make the previous one obsolete, right? Every process kind of brings something new to the equation. For instance, when we went from UMOS 9 to 10, we kept the 175 degrees C rating guarantee, but we brought in better threshold voltage distribution. And this has been really helpful for applications that require a lot of paralleling MOSFETs. That was a huge thing for us, right? It really helped us solidify our place in the automotive space and kind of prepared us well for what we needed in the data center space. However, we recognized further optimizations and RDS(on) reductions were needed. So we took a look at the design, as I'll show you in a bit, and we basically reduced RDS(on) even further, but we kept the benefits from the previous generations as well. As a result, you have a much more robust MOSFET. And you can see here versus some of our competition, this is a figure of merit, right? QG times QoSS, which is more like a switching characteristic, versus RDS(on). And usually when you go better in one area, you're worse in the other. So that's the trade-off, right? So the further you are to the bottom left, the better. And with this UMOS-11 process, we're very confident that it's a very competitive process and it competes with some of the other big players in the industry.
That makes sense. So, talk to me a bit about the performance improvements in particular from UMOS 10 to UMOS 11.
I wanted to give you a little bit of trivia because I think it's a little interesting. You might be wondering, why do we call it UMOS-11? Well, as you can see from this slide, it looks like a U, very on the nose, but it is one of the reasons why this process has been so critical to us because it is a trench FET and it looks like a U. So going from 10 to 11, we basically introduced a much denser channel, and we used this process called a fine strip or a field plate MOSFET technology. And you can see the channels are much thinner than before. So really what this allows us to do is have a much more dense MOSFET. And in order to scale up power, essentially you're putting more of these together in one die. So as a result, the RNA normalized is about 76% of the UMOS 10, and then R on QG, again, another very important characteristic. So you have die size and then the figure of merit, 55% better, which is phenomenal, right? This is a huge jump for us. And again, it really targets some of the most important applications, especially in data center and other markets where efficiency is so critical. So this is the basis to all of these voltages that I showed you earlier. But as you can see, the more dense, the better.
So, Jake, let's talk specifically about SOP Advance, which is a next generation surface mount package for power MOSFETs. What kind of benefits are we talking about with this technology?
This is one of the most common packages, or at least sizes, for a lot of the markets that we work in. 5x6 is very common. It definitely has taken over some of the more legacy, like more pin-equipped packages from olden days, like the 8x8s and stuff like that. 5x6 just makes a lot of sense. So we had a version called SOP Advance. We had a little iteration called Advanced N, which had a little bit different of a heat plate. And now we go to SOP Advanced E, which again, very on the nose. It looks like an E. We're very visual here at Toshiba. But what this actually allows us to do is improve the die mountable area by quite a bit. So this has allowed us to reduce package resistance by about 65%, which is a huge drop. And then the mountable chip size by about 23%. And then that overall gives us a thermal resistance reduction of about 15%. So it doesn't look like much, but that much of a change can actually pay off dividends for all of these applications. So ultimately, a package like SOP Advanced E allows for much higher power density, and that is a very critical thing in modern electronics.
So, Jake, what do you think are the biggest benefits of the UMOS 11H 40 volt series? What does this solution bring to the table?
There's not one MOSFET that fits all applications, right? You might have applications that require better conduction loss or better switching loss or better reverse recovery loss. So with this process in particular, and I'll show you some more details on performance, we really focused a lot on switching losses with this device. However, that's not to say conduction loss isn't better. It definitely is. And the way we achieve that is by better RDS(on). So when we look at a similar class competitor MOSFET, same RDS(on), same package, and about same switching performance or characteristic performance, we actually see about the same conduction loss. But when we look at switching losses and reverse recovery losses, this is where we see some of the best benefits with our process. So for applications where maybe you're switching a little bit more high frequency and you wanted to achieve maybe smaller passives like caps or inductors, So you bumped up the switching frequency. Our MOSFETs will do a very good job in those applications. So it's very much worth evaluating. And I will also note, for a 40-volt MOSFET, this is really being targeted at, say, 12 volts process. And 12 volt is still a very common process among a lot of different applications. In fact, there's a lot of commonality, I would say, between like the automotive space, the data center space, a lot of consumer electronics. 12 volt is kind of a very common backplane voltage. So 40 volt MOSFET really allows us to have a solution for that. And I think this is one of the more optimized solutions for that as well.
How does this solution compare to similar solutions on the market today?
Well, let's get down and dirty with some of these details here because the characteristics really do matter. When we look at temperature, that is one of the key things for applications because we need to guarantee 175 degrees C. But some really underrated features that this includes is a very tight threshold voltage. Sometimes the trade-off between better switching performance is maybe worse threshold voltage, but we're still able to keep this between just 1 volt. And this device, for instance, is intended to be driven at 4.5 volts or 10, your choice, but it's capable of being driven at 4.5 volts. And at that level, we're able to guarantee RDS on, which is lower than 1 milliohm. In fact, it's 0.39. And we don't have to give up some of these figures of merit, like QG and RDS on, very common figure of merit, or switching gate charge, output, and reverse recovery charge. So again, take a look at our similar class competitor MOSFET, also in the SOP Advanced E. So they're taking advantage of this same improved die area that we are. We can actually guarantee better RDS on, better switching performance, better reverse recovery charge in the same device. And this is a huge thing because again, some of these applications require minimal improvements to efficiency can pay off dividends when the cost of electricity or heat generation. So really, I think our product gives you a much more balanced plan of attack to address efficiency concerns in applications.
What about the body diode aspects of this solution? What does that look like?
So believe it or not, the body diode of a MOSFET can actually be really important. We kind of see the benefits of this coming into its own through switching and reverse recovery charge. And because we employ a faster body diode, it's our own unique technology in the device, it reduces the ringing and the recovery waveform. And as a result, when you look at reverse recovery charge over the change in current, Toshiba has much better performance, I would say, over a variety of slew rates. And the same goes for the voltage peak. Very minimal difference, but even that much can be beneficial for many applications because ultimately spikes aren't appreciated anywhere in a circuit. So if you can minimize them by any means possible, it's absolutely worth it. So we're able to include this while not sacrificing in other areas. And this has been a really big thing for us.
So, Jake, how does this solution compare when it comes to thermal characteristics and safe operating area?
And that's honestly one of the key questions, I would say, because when you're using a MOSFET, two things are going to happen. It's going to get very hot, and you need to cool it down. And oftentimes, this is completely synonymous with the safe operating area. Because when you look at a switching waveform, if your device is switching too fast and the temperature is getting too hot, you really risk damage to not only the device, but the entire system. So when we look at some key characteristics like RDS on versus ambient temperature, this is also a very key thing because, again, I mentioned earlier, this device can operate at 175 C, and all the datasheet characteristics are guaranteed at that. And oftentimes customers are using our MOSFETs at high temperature, and all these modern applications have to sit in that range as well. So if you're choosing a MOSFET, you want to choose one that performs better at high temperature. So naturally, RDS-on does get worse at high temp, but I think ours do better than our competitors, which has been really helpful. And we're able to kind of balance that with a few other characteristics like the cutoff current, for instance, breakdown voltage. Ours can be higher than our competitors while keeping a very similar level of gate threshold voltage. So again, we're not having to make some of the sacrifices and characteristics that our competitors are that you would normally see. And that has allowed us to have maybe a more robust SOA. And SOA looks at a few different characteristics like the duty cycle, the period, 1 millisecond, 10 millisecond, or DC. And again, apples to apples versus a competitor, you can see that Toshiba's device does quite a bit better in terms of SOA. And for a lot of applications, they are skirting the line here. So any way that they can stay within regulation there is critical. And I think this really helps them get there.
So, can we also talk about the UMOS-11H 100-volt solution as well? What are the biggest benefits here?
And you might be surprised, but 40 volt to 100 volt is a pretty big jump as well. Our 100 volt is really going to service the 48 volt application, or you might hear this as 50 volt or 54 volt, but ultimately it's a 48 volt backplane. And this is also really critical in data center and automotive. In fact, automotive might be the one that's the most interesting because a lot of modern vehicles are shifting from 12 volt to 40 volt or 48 volt. And as a result, 100-volt MOSFETs are basically needed because when you take into account basically noise, switching performance, you have to give yourself maybe say 50% headroom. You get really close to this 100-volt level unless your process or your design is very tight. So these just make a lot of sense to cover both bases. And benefit wise, it's going to pretty much mirror what you see at 40 volts. However, some of them are more pronounced because maybe some of our competitors haven't gone all in on 100 volts for switching performance. So, definitely improvements in conduction loss, improvements in switching loss, but you'll see the most drastic improvement in the reverse recovery losses, so QRR. And again, for switching applications, and if you're a customer designing for this kind of use case, you will find a lot of benefits using the Toshiba MOSFETs.
So, how does this solution compare to other similar products on the market?
There are a couple, there are some heavy hitters out there. And one of the cool things I think is we're able to come in and win on performance alone sometimes. So it gets a bit more pronounced. 40 volt, some of the differences were very minuscule. But when you look at 100 volt, that's when you can really see this product shine. So again, one of the key trade-offs you'll typically see is RDS on and reverse recovery charge. And versus our competitors, we can maintain about the same RDS on while reducing the reverse recovery charge by quite a bit. Then we look at things like gate charge and switching charge, and we see overall some pretty big benefits to using our device. Now, you might notice this nomenclature sometimes. You'll see it's UMOS-11 HSD. HSD stands for high-speed diode type. We might have versions without that, which would be a standard type. And really the difference there is, does it have the fast body diode? Does it not? And the purpose for that ultimately is some applications just don't need the fast body diode. Some of them might benefit more with just pure RDS on reductions. So the cool thing is Toshiba offers that flexibility, and it gives designers a reason to look at several devices from us and hopefully settle on the one that suits their application the best. When we look at comparison data, we look at efficiency measurements. And I mentioned this earlier, but minuscule improvements in efficiency can pay dividends, especially as you're working in very high power, say data centers, for instance, where maybe you're doing eventually 1 megawatt racks. And a change of 0.23% of efficiency is huge, right? When you're paying for electricity and you're generating heat, this kind of reduction can mean worlds of a difference for those kind of applications. So when we look at our device versus two other competitors and a Toshiba competitor internally, we offer better efficiency. So we look at output currents from 4 to say 18 amps, and we can see improvements up to 0.23%, and then at the high current range, 0.05%. But believe it or not, that is a huge gain. And there's definitely good reasons to consider this. So two different topologies that we tested, 1 kilowatt isolated DC to DC. This has been a very typical application. In this case, it's 54 volt in and 32 volt out. Or in the case of 1 kilowatt buck boost, 48 volt in, 14 volt out. And under this test condition, we saw similar levels of efficiency improvements across the board. So again, if you're a designer and you're looking to maximize your circuit performance and you want to try out something new, take a look at Toshiba. I think you'll be surprised.
So, Jake, what role does the 80-volt process play in modern designs, and how does it compare with other competitors?
Again, I mentioned this earlier, 100 volt covers the 48 volt range. What could the 80 volt cover? And 80 volt actually can cover the same thing at 48 volts. It really depends on how optimized your circuit is. If you're able to have lower headroom, you actually do see a nice jump in performance. And typically, the closer you can get to your actual working voltage with your MOSFET, the better performance you will have. We see a maybe 10 to 20% drop, for instance, in RDS on when you go from 100 to 80. And the result of that you can see below. So conduction improvements still there, switching loss improvements still there, and same with reverse recovery loss. So as a result, when you look at versus our competitors, we keep some of the same benefits, especially when it comes to RDS on, one of the key figures of merit. And we look at gate charge and then all the way down to reverse recovery charge. And overall, we're able to balance this trade-off much better than our competitors. And again, this really does pay dividends in many applications. So one bit of data, you'll see these graphs here, and we look at ambient temperature, RDS on, similar to some of the previous graphs I showed you, break down voltage and cutoff current. And Toshiba kind of stands out on its own. It's been really nice to see a product come into the market so strongly and be able to compete. So again, efficiency is a critical thing. We've tested these apples to apples, and we're confident that this device can be a winner in your application.
Jake, walk me through a typical application.
You know what, Amelia? This is one of the best applications to look at because data center, AI data center, you probably can't stop hearing about it. And to be quite frank, Toshiba hasn't stopped thinking about it because there's a lot of really interesting things that go on. And I'm not going to bore you with all the minute details. All you really need to know is simple, right? You go from high voltage, from grid, down to what's going to be 800 volt in the future, 800 to say 54 volt, 54 to 12. So every single one of those steps requires a lot of conversions. And specifically here, we're going to focus on the conversions from say 800, 54, and then 54 volt to 12. And I mentioned this earlier with efficiency. If you improve the efficiency on all of these subblocks, we're going to call them high voltage IBC and low voltage IBC. This is going to pay dividends in your applications, generate less heat, and improve the overall efficiency. So Toshiba's UMOS process is going to support those core voltages, 54 volt and 12 volt. So as I'll show you in following slides, we can offer distinct suggestions for these applications. But I will just note, Toshiba supports a wide variety of these applications outside of just our low voltage MOSFETs. We do offer silicon carbide, eventually GaN, and a wide variety of other voltages for all kinds of use cases within data center.
So, Jake, I'm curious about the high voltage IBC you just mentioned. Can you talk about that solution a bit more?
Sure. And this is going to be one of the most important building blocks for modern data centers because as I mentioned earlier, there's a big shift to 800 volts, right? A lot of the big players have settled on this as a means to reduce overall inefficiencies. So a lot of the backplanes are jumping to 800 volts. And naturally, we have to step down. So 854 right now seems to be the most logical solution. And in that case, we have a few different ideas of how we get there. So we have two-level, three-phase LLC, maybe a three-level, three-phase LLC. But at the core of this, you're going to have two sides, right? Your primary side is going to be high voltage, 800 volt, and then your secondary side is going to be 54 volt. And 54 volt is going to be servicing the 48 volt backplane, basically. So for that specifically, that's where Toshiba comes in. We might have a full bridge type, in which case for a full bridge, we're going to recommend one of our 80 volt processes, like I showed you earlier. Or maybe if we do a center tap type, you're now splitting this over a couple different FETs. So we recommend 150 volt. So as a result, our process works very well here. And we have flexibility on a lot of different ways. So whether it's RDS on or package, there really should be a Toshiba proposal for any of these. So below, you definitely take a look, but there are some specific figures that I call out in terms of what is better about our devices. Definitely worth considering for these kinds of applications.
So, what about the low voltage IBC? Can you give me some details about this one?
Low voltage IBC is just as important as the high voltage because ultimately this is going to get you down to 12 volt. And I mentioned 48 volt is kind of the new standard for data center, but 12 volt is still there. You still have to get down to 12 volt. There's still a wide variety of applications, especially around storage, memory, and even all the way down to the GPU where 12 volts is critical. And you might even down convert again, but there are some really specialized solutions for that we won't really talk about today. But on that primary side, you still have a strong need for silicon MOSFETs. For instance, HSC is a hybrid switch capacitor converter. This is I would say, common topology that's a bit newer, but you have like three tiers of MOSFETs. So we look at this from left to right. If you tilt your head a little bit, it'll be high to low, but ultimately you will have kind of two classes of MOSFETs needed, which would be 80 volts on the upper two and then 60 volt for the lower two. And with this topology, Toshiba does quite well because again, you have this flexibility of package. Let's say you don't have a lot of room to work with. Well, Toshiba can come in with our 3x3 device. Or, if you're looking to maximize just sheer performance, that's when maybe our SOP Advance E can come in. Or let's say you want better cooling, we can throw in the dual side cool device as well. So for the HSC topology, I think we have a really great solution. But we recognize that's not the only approach going from 54 to 12. There also might be multi-phase buck converters or simple LLC. In any case, our MOSFETs have been designed to kind of address these concerns specifically. So I think you'll be surprised when you try out your FETs in these kind of topologies.
Jake, what about automotive? How does Toshiba design MOSFETs for this market in particular?
Some of the core tenants are there, but there's a lot of new things that we have to do in the automotive space to really win. And one of the most important things, of course, is bringing the process over while maintaining high reliability. So you might be familiar with the term AECQ. And this is a very simple standard that says your device needs to be tested rigorously, has to achieve these specific temperature tests, pressure cookers, operation lifecycle tests, has to guarantee all these things. But Toshiba looks at that as a baseline, right? We look at that. We think internally we should do 2 to 3 times better than that because oftentimes all applications are expected to last in the market for a very long time. So you'll see in some of these side-by-sides, we sometimes even do tests that aren't included in AEC-Q. But it does require us to build a much more robust MOSFET process, which we have done with UMOS-11. You're going to notice some of the same benefits versus our competitors that I showed you in the previous sections. It's just now these devices are automotive quality. They're ready to go in all kinds of high temperature, intense applications for 40 volt, 80 volt, 60 volt, and 100 volt MOSFETs, and some actually different packages as well. So you'll notice the 3x3 still here, the SOP Advanced, the dual side as well. And this has what we call a wettable flank. So you'll notice that in parentheses WF. This just helps with soldering and optical inspection, which is a pretty critical thing for automotive. But now we introduced two new packages called S toggle and L toggle. And these are surface mount packages. You might recognize a toll package. This is a version of that which has gull-wing leads. And we've talked a little bit about temperature, but when the devices are getting really hot and you don't have gull-wing leads, what ends up expanding and contracting with the temperature is actually the solder, and we don't want that, right? So by introducing these gull-wing leads in a larger and smaller form factor, this allows us to mitigate that concern of the solder cracking, and instead the gull-wing leads themselves will expand and contract. So again, reliability is an important thing for Toshiba, and all the products I showed you earlier that aren't necessarily automotive grade actually do go through a very similar level of reliability testing. However, all the automotive ones are guaranteed for AEC-Q. And there's a lot of really important applications for that as well.
So, what kind of applications in the automotive space are good fits for Toshiba MOSFETs?
Amelia, you'd be surprised. There are a lot of MOSFETs in vehicles. So I've called out a few applications here. And really, we have to consider two paradigms, right? Full EV and maybe hybrid EV. Because in both cases, the semiconductor count in vehicles is just exploding ultimately. Because as everything gets electrified and more things get modernized, there's just a strong need for MOSFETs in general. You have battery voltages that may range from, simple 12 volts lead acid battery all the way to 800 volt lithium ion. And you kind of have to design around all of that. So when we look at things like onboard charging, off-board charging, both of those, hey, need MOSFETs. Battery management, if you need to control the battery in your vehicle, also a lot of MOSFETs. Surprising application that we see actually quite a bit of success in, for instance, is electric power steering, because ultimately it's a giant motor. And if each pole has, say, 6 MOSFETs and you have redundancies, you're hitting 50 plus MOSFETs in one electric power steering column. Relays, junction boxes are also becoming semiconductor based, and those use MOSFETs to switch. Inverters, brakes, starters, engine, windows, doors, LED headlights. The common thing among all of these applications is the requirement for high efficiency, small MOSFETs. So really this aligns with what Toshiba has been doing for many years. And it's just more proof that this is the direction that we need to innovate as a company and invest our technology in, because these aren't going away and they need to be better and better.
So, Jake, what would you like my audience to take away from today's Chalk Talk?
Thanks, Amelia. And I really appreciate the time today. I really hope you enjoyed what I showed you, and I hope it was interesting for you. But I want you to take away a few key things, right? Toshiba is a long-term MOSFET supplier. We offer competitive low voltage power MOSFETs. Hopefully you've seen that here. Ultimately, high efficiency, low voltage MOSFETs are critical for maximizing performance in many modern applications beyond the ones I even just showed you today. And ultimately, Toshiba is investing in the next gen processes like UMOS-11 and packaging like SOP Advance E. You can continue to expect great innovations like this from us over the years. And hey, all current and future UMOS-11 MOSFETs can be found on Mouser.com.
Fantastic. Well, Jake, I think that's all I have time for today. Thank you so much for joining me.
Thanks, Amelia. It's been great to be here.
And before we go, you didn't forget to click that link, did you? There you can find even more information about this topic from Toshiba. For Chalk Talks, I'm Amelia Dalton from eejournal.com. For more Chalk Talks, head on over to the Chalk Talk section of EE Journal. You can't miss it, it's right across the top. Or head on over to YouTube, youtube.com/EE Journal.